Hello. Our topic for today is modeling a power grid system using PSCAD. Our advisor is Professor Monemi. My name is Nico, and I'll be starting us off. Goals. For our senior design project, we wanted to dive into and learn more about power systems to get some experience using software that researchers and engineers utilize for design, simulation, and analysis. Our project aimed at designing a power grid model using components on PSCAD for power generation, transmission, transformers, generators, and distribution to 3 different consumer sectors of the power grid. We also wanted to utilize power system calculations to measure and analyze our results in order to verify our measurements and design parameters. What is a power grid? The power grid is an interconnected network for transporting electricity to consumers. The power grid can contain many different components, including generator stations, substations, transmission lines and towers, and individual consumer distribution lines. For designing the power grid, we considered the ability to provide sufficient electricity to various distribution loads by maximizing the power delivery by implementing shunt capacitors, prioritizing the safety of consumers by implementing a fault system, and provide stability throughout the design using a generator.
And now that Nico explained to you how we design a power grid, I'm going to be talking to you what software do we use to design our power grid. For this project, we mainly focus on using PSCAD to simulate a power grid. PSCAD stands for Power System Computer Aided Design, and it's a very powerful and flexible, user-friendly graphical interface that the industry currently uses. It enables the user to build a circuit, simulate it, and analyze to measure the results. This software was made by the Software Development and Engineering Department at Manitoba Hydro International. PSCAD is used by many researchers and engineers in the industry to help aid them in their fields of expertise. The software typically helps in the design stage, in which a power system is created, and the simulation or the analysis stage, in which the software is used to test the integrity of the design to see how well it will behave in a real-world scenario. The power grid that we design revolves around 3 different sectors. We have the residential sector, industrial, and commercial sector. Now, the first sector that I'll be talking to you about will be the residential sector. And as many as you know, residential areas are the designated place for us to live in. And our power grid provides power to a mini subdivision which consists of 8 residential homes. And these 8 residential homes were separated into 2 groups of 4 houses. As you can see on the picture at the top, that would be typically what you would see if you're seeing that in person. And the picture on the bottom is what we designed to look like on PSCAD with those 4 houses there. The typical voltage in residential home is 120 to 240 volts. And we gathered the data from specific residential applications to model residential homes from a research paper sponsored by the National Science Foundation. We wanted to use power consumptions that would typically be seen in residential buildings. In this case, we have 0.5 kVAR and 1.63 kilowatts per phase. And residential loads typically consume less power individually when you compare it to other sectors, but in the United States, residential loads typically consume more than commercial sector load, as there are just more houses out there when you add them all together.
Hi everyone, I'm Wen Chen Gu. In this slide, we are introducing the industrial load. An industrial load that is require a lot of power to run. For example, the large office requires 286 kW per phase. The industrial loads that we decide to include in our projects are boiler, batteries, General Motors, and the aggregate load. These are the 5 loads for industrial load. Each has its own power consumption. The 2 smaller loads shares a bus, and the rest have their own individual bus to do. So the next will be the commercial load.
Hello, my name is Martin and I'll be the presenter for this slide. The commercial load design in the PSCAD simulation is made up of 3 different components. The data for each of the buildings making up the commercial section were researched, and a simulation was done in PSCAD as shown in the image. The simulation of the commercial building consists of 3 different buildings: a retail store with a food service facility, a distribution center, which is a warehouse, and a public assembly building, which is a library. The power consumptions of each building were researched from the California Energy Commission. There were calculations done to improve the power factor in order to reduce loss and improve the voltage regulation. These calculations will be explained in the next slide.
Now, one of the ways that we made sure our power system was running as efficiently as possible was because we made power factor correction calculations. Now, power factor calculation translates to improving the efficiency of the system as a whole. So the way we do that is we have our power factor triangle here. Now, our S, or hypotenuse, represents our complex power in kVA. We have our real power and the x-axis here in kilowatts, and then lastly in the y-axis we have a reactive power in kVAR. So what happens is our loads, they're reactive loads, and they're consuming reactive power. And they're consuming so much reactive power in comparison to the real power that our angle is so big, making our power factor low. So what we want to do is we want to bring that Q value down. How do we do that? We implement a capacitor in parallel, because when we do that, it brings up the idea that we have negative reactive power. So when we add those Q's together, it will reduce the total size of the Q down, bringing our angle much closer to 0 as possible. And when we do that, it increases our power factor. And once we do that, we find the value of the Q that we need to find the value of the capacitor that we will need to implement into the circuit in parallel to bring our power factor up back to 1 as we wanted to.
Hello, my name is Brian Vargas, and I'm going to be talking about our day calculations and our night calculations. The demand for power is different depending on the region's population density. To keep the grid balanced, there must be enough power to meet the demand. The demand is studied by the generation operators. Since the demand is not constant, during peak hours, peaking power plants gradually come on and provide extra power that is needed. Natural gas power plants are an example of peaking power plant since they have a faster startup time compared to coal plants. The downside of this faster startup is that it has higher fuel cost. Typically, coal plants can take 12 or more hours to start, which makes it good to satisfy the baseload demand, and is why we chose the coal plant for our source. So for our day calculations, you can see that we calculated the current from the values, and then we also measured it in the software, and calculating the percent error, we got 2.87. So the difference between our day calculation and our night calculation is that for the night calculations, for simplicity, the industrial and the commercial load were removed, and we just compared the current between the day and the night residential load. The percent is 0.42 higher on the night schematic, and this is due to a higher current going to the residential load.
Hello everyone, now I'll be talking about the generators and why we implemented for our project. In electrical engineering, particularly in power productions, there are 2 main sources of energy conversions. First is the motor, and the second is the generators. The generators have 2 different states. You can use it to operate like a machine, or you can use it as a source. Generator is a device that produces electrical energy. The synchronous generator is an AC generator and is used for energy generations by wind turbines, steam turbines, and hydro turbines. All of these models are included with the PSCAD softwares. And the generator is also known as the alternator, which it converts the mechanical energy power into electricals. The synchronous generator is now a self-start machine, so you must connect it with the external source, and it is supplied by a DC source. This is called the DC excitations. And the power system, and our system also has a power system stabilizers, which it helps reduce the input-output power swings and improve the system stability. And this also comes in the software. It is already pre-built. Next slide. Besides day and night calculations, we also did the transmission line analysis for our grid. The goal is to express the voltage and current at any point along the line using the two-port networks. Based on our grid, we're able to use the coupled pi section to demonstrate short lines with 25 kilometers. And the coupled pi sections also included the series impedance, shows in the left corner. The line is observing 208 volts at one of the sectors. And suppose that we want to raise the power factor to 0.9 at 10 MVA for the transformers, which is uniform throughout the systems. We're able to find the ABCD parameters and using it to find the source voltage and the source current. This slide shows one of the residential sectors for our power grid. By finding the ABCD parameters, we're able to find the source voltage without knowing the systems and how it behaves. We're basically treating it as a two-port network. Pictures on the right shows the voltage of the load and the voltage of the source, which helps us to identify if our calculations will match or not. So knowing the ABCD parameters for a short transmission line at 25 kilometers, we're able to find the voltage of the load and current of the load easily. And plugging into the formulas for the source voltage is shown below. Vs is equal to AVR plus BIR. You plug in those ABCD parameters and you can get the source voltage easily. And that is the phase voltage. And if you convert it to the line-to-line voltage, you just multiply that number with a √3, and you get 207 at angle of 2.288 voltage.
Hello everyone. Now we're gonna talk about how our power system design will have a positive impact on our society. First, economic impact. Power grids can impact on our society by transporting energy, which can lead to the creation of new businesses, jobs, which provide more opportunities for individuals to earn an income and lift themselves and their family out of poverty. Second, we have global impact. Power grid is important around the world to provide power to the people and fix problems to have a sustainable development. According to Ricci, a researcher from Our World Data, about 940 million people around the world do not have access to electricity. And with this power system design, we are hoping that with this knowledge, that we would create a beneficial way to help them have access to electricity one day. And third, environmental impact. The three most common natural electricity resources are natural gas, nuclear power plant, and coal, which have negatively affect the environment in various ways, such as emission of greenhouse gases when fuel is burned, use of water resources to produce steam, and providing cooling and affect the ecosystem because of the waste it produces. With our power system design, we are hoping to install a clean energy in the future, which can help preserve our environment and avoid those negative effects to our ecosystem. Fourth, impact welfare and general safety. Our power grid system can be threatening to public health and safety because of high voltages it stores. One of our top priority is the health and safety of our customers, and our system has a built-in protection zone. These protections consist of circuit breakers, relay, surge protection devices, and fuses. These safety measures are spread out all through our design and can help prevent anomaly, like disastrous events on our design.
To conclude our presentation, we were able to meet the goals that we set forth by 100%. We were able to create our PowerGrid schematic in one PSCAD case file and modeled all the parameters I mentioned in our goals. With the schematic, we were able to enhance our knowledge of power system calculations and important parameters to take in mind when designing. Future work could entail different analysis scenarios of a power grid. On top of that, future work could also include looking into more topics that can be researched with PSCAD, like renewable energy. Thank you so much for listening to our presentation, and thank you so much to Professor Monemi. Have a great day.